Hello, in this video we want to compare the classification of discrete time models versus continuous time models. So as a reminder, our discrete time models are often written as difference equations, and the continuous time models, those are really our differential equations. Okay, so the first classification is to consider whether you're working with a first order or a higher order model. So recall back in the land of discrete time models, a first order model was one that only involves most recent past state variables. So if we're looking at x sub t, our model only is a function of x sub t minus 1. Whereas a higher order model would have x sub t minus 1 and additional past states like x sub t minus 2 or x sub t minus 3 and so forth. So it looks farther back into the past. And that's pretty similar to what we see with the differential equation. So a first order differential equation is only looking at the first derivative, so we're kind of looking only at changes in x with respect to time, only the first derivative, how that rate of change is written, and that's our right hand side. And then a higher order differential equation involves higher order derivatives. And so you can think about like the second derivative of x with respect to t and so forth. The next way you might classify the models is thinking about whether you've got an autonomous model or non-autonomous. So back in the land of discrete time models, an autonomous model does not explicitly involve t, whereas a non-autonomous model would involve t. Similarly, for continuous time models, it's the exact same sort of. Lastly, linear versus nonlinear. So recall that back in discrete time models, a linear model has only the highest exponent on the state variable being 1. And then if you've got higher exponents, or you've got nonlinear functions like trig functions or things like that, that would be a nonlinear model. And then the same is true over here in differential equations. So for example, dx dt equals 2x plus 4, that would be a linear differential equations, where something like dx dt equals 2 sine of x plus 4, that would be nonlinear because the sine function is a nonlinear function. Okay, so techniques for solving differential equations. This is not a class in differential equations, so I'm not going to go into a lot of detail here, but I do want to give you an overview so that you at least understand the context within which we're working. So the idea of solving differential equations is that you're given an equation with a derivative in it, and you want to try to retrieve the original function. Okay, so let's think about dx dt equals t squared, and if this is a little bit weird because x is usually an independent variable, you might want to think about dy dx equals x squared. Okay, so you could call the variable something different so that it looks more familiar. But if somebody walked up to you and handed you this differential equation and they said, okay, please write x of t for me, well, you could solve this by saying x of t equals 1/3 t cubed plus c. And so I just integrated here, and you could go back and check this. If you did x prime of t, right, if you did the derivative with respect to t, you would certainly get back your function t squared. So integration is kind of this idea of lifting off the derivative. Now sometimes they get more complicated. For example, if you had something like dn dt equals 2n, we can't quite integrate with respect to t on both sides because we've got n over there on the right hand side. And so this involves a technique called separation of variables. I don't expect that you've seen this if you've only had a Calculus 1 class, so I'm just going to give you an overview here to show you that there are techniques for solving these equations. So the first step in separating the variables would be to divide both sides by n, and then we can also separate the dn dt, so we get 1 over n dn equals 2 dt. Now we can integrate both sides, and when we do that we get natural log of the absolute value of n equals 2t plus c. Assuming n is strictly greater than 0, we can drop the absolute value sign, and now exponentiating on both sides, we have e to the ln of n equals e to the 2t plus c. On the left-hand side, we have n, and on the right-hand side, we have e to the 2t times e to the c. And we could rename that last factor there with k, so k equals e to the c. So that would be one way of solving that. And again, I don't expect that you're an expert in differential equations or that you've ever seen them before. I just want to show you that there are techniques for starting off with an equation which has a derivative in it and working through and retrieving the original function. So our focus here will be, first of all, deciding whether we want to use discrete models or continuous models, and then if we're using continuous, really how to simulate them on the computer. So we won't be solving differential equations by hand or analytically, we will be using the computer to simulate them. So here's some points to consider. First of all, linear differential equations are always analytically solvable, where nonlinear equations don't always have an analytical solution. And when you're building a model yourself, it may be easier to conceptualize a discrete time model. It's kind of easier to think about the components and what's happening step by step. And once you've got that discrete time model, then you could connect this to a continuous time model if that's appropriate for your system, and make it more elaborate. Here's where we're going to focus. The discrete version of these continuous time models can be simulated on the computer, and that's what we're going to do, and that's often what you need to do if you don't have an analytical solution available anyways. Now, there are some ways in which you could get numerical errors and places where you have to be careful here when you simulate things on the computer. That is the topic of a course at UVM called Numerical Analysis, which is a great class. But we will just be, introducing ourselves to this topic of simulating continuous time models on the computer and exploring some of the techniques in that area.